You know, have you ever wondered how we actually know exactly what our soil is made of? Well, welcome to this explainer. Today, we are diving into the precise mechanics of soil particle size analysis. Some folks call it mechanical analysis, but basically it's how we discover the exact physical makeup of the ground beneath our feet. But as you'll see, it relies on some incredibly strict lab procedures and some fascinating, but honestly pretty flawed physics. Let's get right into it. Here is our roadmap for today. We're going to start with the basics of particle size analysis, then decode Stokes' law, compare those neat theoretical assumptions against messy reality, and finally, look at the real-world significance of soil texture. Moving right along. Okay, Section 1. Let's look at the physical prep work required before we can actually analyze any soil particles. So, before any true analysis can even begin, we've got to follow these 3 strict lab steps to isolate the fundamental particles. First up, we have to completely clear away the bigger stuff, like rocks and rubble, by screening the soil through a 2mm sieve. Then, step 2 targets the humus. We literally have to destroy it using oxidizing chemicals, like hydrogen peroxide. And finally, step 3, we chemically strip away any lingering binding materials using solutions like calgon or sodium oxalate. We are essentially breaking the soil down to its absolute bare bones components. Now, this is absolutely crucial. If we fail to fully separate these particles, we fall into a massive analytical trap. I mean, think about it. Lumps of clay that remain stuck together, they're going to act and look exactly like sand, which means our final results will completely misreport clay aggregates as sand, basically ruining the entire analysis. So our core objective here is pretty straightforward. We need to determine the exact percentages of sand, silt, and clay. And to do this, we generally use the pipette method or the Bouillot hydrometer method. But what's really fascinating is that both of these methods rely entirely on the differential settling rates in water. It literally all boils down to one simple physical fact. In a viscous fluid, larger particles are going to plummet a lot faster than smaller ones. Which brings us to Section 2 and the underlying physics that actually governs that differential settling rate. Enter Stokes' law. All right, so according to Stokes' law, the terminal velocity of a spherical particle settling under the influence of gravity in a fluid of a given density and viscosity is directly proportional to the square of the particle's radius. Okay, that's a mouthful. In simpler terms, how fast a particle falls depends entirely on this delicate mathematical dance between gravity, the thickness of the fluid, and the exact size of the particle itself. To actually calculate that terminal velocity, we have to map out a perfectly balanced equation. We're looking at how the settling velocity interacts with the particle's radius, how dense the solid particle is compared to the fluid it's falling through, and of course, the overall viscosity of that fluid. All right, let's move into our third section and see what happens when the perfect mathematical assumptions of Stokes' law crash headfirst into the messy reality of actual soil samples. Our first big reality check is particle shape. The math strictly requires these particles to be perfectly spherical and perfectly smooth. But in reality, a lot of colloidal particles are actually plate-shaped, and because of that flattened structure, they kind of flutter down a lot slower than a spherical particle of the exact same mass. So right out of the gate, our velocity calculations are skewed. Next up, the law assumes uniform density across the board. But the heavy reality is that soil particle density varies wildly. Your standard silicates sit around 2.6 to 2.7 grams per cubic centimeter. But heavy minerals, like iron oxides, they can easily hit 5.0 or more. That is a massive discrepancy when your entire mathematical calculation relies on a uniform weight. We also hit a literal microscopic wall. The math assumes particles are large enough to just fall independently. But once you get particles smaller than 0.0002 millimeters, they start exhibiting thermal Brownian movement. Basically, at this tiny scale, the fluid molecules themselves literally intercept and bounce the soil particles around like a pinball machine, completely disrupting their downward fall. And finally, Stokes' law requires that particles don't interfere with one another. It assumes an unhindered, independent fall within a perfectly still suspension. Reality, as you might guess, is way more chaotic. A lot of the fast-falling particles actually create drag and physically pull finer particles down along with them. And on top of that, any particles larger than 0.08 millimeters settle so fast that they create turbulence, completely ruining the perfectly still suspension we need for an accurate measurement. Okay, with our lab analysis complete, Let's zoom out to the macro level for Section 4. Let's explore exactly why determining these exact percentages of sand, silt, and clay is so incredibly significant in the real world. So why go through all this trouble? Well, because the texture we uncover in the lab is highly practical. Out in the field, it literally dictates the actual value of the land. It determines the land's capability and tells us the specific soil management methods we need to use. It tells farmers exactly what crops will survive in different seasons. It acts as the most stable, reliable index we have for the true agricultural potential of any given soil. But it goes way beyond farming. This texture dictates absolutely critical soil physics. It determines the pore space within the dirt, which controls how well that soil holds water, air, and nutrients. It even impacts the soil's temperature. And from an engineering standpoint, this analysis literally decides if the ground is stable enough to hold up building foundations or a new highway. It's a real make-or-break metric. For scientists who are mapping our environment, texture is the absolute cornerstone. It tells us exactly how much amendment is needed if we're trying to reclaim damaged lands. It's also totally crucial for understanding soil morphology and genesis, which is essentially the story of how the soil formed in the first place. That allows for really accurate classification and mapping across different regions. However, as powerful and useful as this analysis is, we have to acknowledge its absolute greatest shortcoming. Mechanical analysis entirely measures size. It absolutely does not account for differences in the type of clay present in the sample. And that's a huge deal because the specific type of clay is absolutely decisive in determining how a soil behaves. So this limitation leaves us with a pretty massive lingering question. If our analysis only reveals the size of the particles, but entirely misses the actual identity of the most reactive components, what vital secrets is the soil still hiding right beneath our feet?